Hello everyone, myself Dr. E. Kumar Swami. We are discussing topics on digital image processing. Today's topic is sampling and quantization. So with the help of the capturing device, we are converting the light energy into electrical so that image is in the form of continuous. So where that continuous image is going to be digitized by using these following two steps. One is sampling, other is quantization. As we already discussed that an image is represented mathematically as a function of f of x comma y, where x comma y are the spatial coordinates and f is the amplitude at that coordinates. So to convert these x comma y coordinates and the amplitude of the coordinates is going to be converted into digital form. So here we are having the process of sampling and quantization, where the sampling is converting the spatial coordinates x and y into discrete values. So after converting the spatial coordinates into discrete values, the amplitude or light intensity at the coordinate is going to be converted into digital form. So the process of discretizing spatial coordinates, in short, we call sampling. The process of discretizing the intensity value or gray level values is called quantization. So that after passing through these two steps, the continuous image is going to be converted into a digital image. So here we consider a simple example here, an image of some shape of the object. Here consider some L shape. Here where we focus on only a one line which is from A to B. So observe the figure 1. In figure 1 is the continuous image, in that we are only interested to convert this line A to B into digital form. For that we are here using sampling and quantization. So first we are going to get a scanned line of this AB based upon the intensity values. So for that we just get the scanned line in figure 2. So as observing from A to edge of the object, the light intensity is white, so it is at eye level. From the other end, right side, from the object end to B, again it is a high level, so we are getting this high value. So this high value is this, these are the high values. So you can observe here the high values are here. I am going to marking, this is the area. So this area indicates that the background is white. So here it is white, means high level. And coming to here, from this edge to this point, the background is white, so the intensity level is high, so that is marked here. And in between this portion, so from this edge of this object to the complete this other end, this portion is, as you observe, at the middle there is some light intensity is increased, and at these edges the light intensity is low. So as that is going to be represented here, this. So this is the edge point. As moving in the center of the object, the light intensity is little bit increased in this image. So as moving away from that, again the intensity is decreased here. Okay, so that is what here we observed. So this indicates that this only A to B scanned line is available here. Here we get some disturbances, that is because of some noise. So we'll get some change in the intensities, but which is very minute. So now here we are going to convert this scanned line of A to B into digital form by performing sampling and quantization. So here on x-axis, here we are performing sampling by taking the samples at equidistances. Here it is the point at which we are taking one sample, and this is the second point at which we are going to take second sample. So these samples here marked with very tiny square boxes. This is my first sample. So here we are marking these points are the instances at equidistance. We are going to take the samples. So here you can observe, this is one square box. At this instant we are taking one sample. This is the second square box at the second sample, and this is the third square box, we are taking the third sample. So likewise here we are maintaining equidistance marks time marks. At these instances we are marking the sample. So here it is one more sample, here this other sample. So at each and every mark we are marking the square boxes. Here these you can observe here very small square boxes, means you are taking the samples here, right? So this is what we are taking samples at this rate. So once you are marking these samples, again here also this is 1 2 3 4, so here 4 samples. Okay, these are the other samples, and left side also we are taken 4 samples, so that all the samples are discretized with the process of sampling. Now these sample amplitude are going to be quantized by using a quantization process. So depending upon these intensity levels, here we consider 8 levels from complete 0 to complete white. So here we go with a 3-bit code is assigned to each gray level. So that is the reason there are 8 levels from 000 to 111. So based upon that we are assigning the code word to each sample value. Once we assign the code word, now it is called as a digital scan line. So with that we are converting a continuous scan line of AB into a digital scan line. Okay, so by performing these points as we discussed in this previous slide, the one-dimensional function is a plot of amplitude which is shown in a figure 1. That is going to be scanner line is get in figure 2, and in figure 3 we perform sampling and quantization, and in figure 4 we got the digital scanner line. Okay, so the same steps are here I shown in these slides. And coming to this, when you perform all the lines you are going to get a digital image. So this is our a figure, this figure is our continuous image that is going to be digitized by using this sampling and quantization. That's the entire image, where we discussed in earlier that is only for one scanner line, that is performed for entire image. You will get this digital image. So while performing this sampling and quantization, we need to taking these points in the taking of these samples, at what rate you are going to sample. So for that, we are defining a smallest number of discernible details in the image is generally defined as a resolution. So here the spatial resolution is at what rate we are going to take the samples, and what is the smallest discernible detail in the image, here we call a spatial resolution. So in this, if we took very lesser number, just like our aliasing effect in one-dimensional signal point of view, if you took the samples less than the Nyquist rate, so then there is a overlapping of spectral components in the frequency domain. So those overlapping components are going to be causes to there is a problem to reconstruct the original signal in case of signal processing. So coming to in the image processing, if we perform the sampling rate is very low, that is the quality of the image is going to be less. Due to that we are getting some checkboard effect. So this is some checkboard effect, and when the amplitude of the gray levels are very means we are going to convert that into few levels. So the number of the or the smallest discernible change in the gray level you can define as a gray level resolution. But if the quality of the image is reduced because of when we go with the very less number of gray levels, so in that case we get some false contouring. This is the problem when we go with lesser number of digits to represent gray level resolution, and earlier one is the checkboard is the effect because of a lesser number of the samples are taken. These are the two problems. So by keeping these points into mind, we need to convert a continuous image into digital image. Thank you.